Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use Coulomb's law to find the force exerted on a charged particle. So what I'm going to do here, I've got a system of charges that I've got labeled Q1, a positive charge right here, Q2, a negatively charged particle, and Q3, another positively charged particle. And what I'm going to do in this example is demonstrate how to find the net force on one of these charges. And I'm going to pick one at random here. I'm going to find the force exerted on charge 2. So the first thing we do is we draw force vectors. And you just take these one at a time. So right now we're going to talk about how these two interact. All right, so charge 1 is going to be attracted to charge 2, so the force exerted on charge 2 is going to be to the left. And I'm going to call that, how about F12, for the force exerted between charge 1 and charge 2. All right, we'll use Coulomb's law to calculate that here in a minute. All right, before we do that, however, now we're going to consider this pair of charges. The force exerted on charge 2 from charge 3, and again, charge 3 is positively charged, so that force is going to be to the right. And I'm going to go ahead and call that F31, I guess. That's the force between 3 and 1. Now, I know that force, 3-1, is going to be a little less than, let's see, 3-2, not 3-1. Force 3-2 is going to be a little less than 1-2 because charge 3 is only 1 microcoulomb, got that listed over here, and it's 30 centimeters away instead of 20. So that pretty well guarantees that force 3-2 is going to be bigger than force 1-2. All right, now when I add these, they need to be added vectorially. So I'm going to go ahead and add these, and I'm just going to call left positive because I know that force 1-2 is larger. So the net force is going to equal F12 minus F32. Now, the F12 is positive because F12 points to the left, and I've defined left as positive, which is perfectly fine. Had we done right positive, it would be minus F12 plus F32. The only thing that matters is that you're consistent. Now I'm going to go ahead and put in numerical values here. So this is going to equal F12 by Coulomb's law. I'm going to write this over on the corner. Remember the Coulomb's law is F equals K Q1 Q2 over distance squared. Right, so for F12, that's going to be the Coulomb constant, 9 times 10 to the 9th. Oh, I'm going to put a little NCU here as well for note consistent units. I'll go ahead and put the units in the correct put all the numbers with their correct units when I put them in to shorten my writing. Okay, so charge 1, and look over here, charge 1 is 3 microcoulombs. That's 3 times 10 to the minus 6 coulombs. That's what micro means. Okay, times charge 2, which is 5 times 10 to the minus 6 coulombs. Now, I'll talk about why I didn't use the minus sign here in just a moment. Oops. Charge 3 is positively charged there. I don't know why I put that minus sign, but anyway. All right. Divided by 0.2 meters, and that's being squared. So that's how we would calculate F12. K Q1 Q2 over distance squared. All right, all in the appropriate units. Minus F32. So that's going to be 9 times 10 to the 9th. That's the Coulomb constant. Times charge 3 is 1 times 10 to the minus 6 coulombs. I'm getting that from right over here. Charge 3 is 1 microcoulomb in my example. Right, times charge 2, which is here, 5 times 10 to the minus 6 coulombs. All right, and that's over 0.3 meters squared. Now I want to talk a little bit about why I'm not using minus 5 times 10 to the minus 6 coulombs for charge 2. Right? Charge 2 is negatively charged, as we see this value here. We used that minus sign when we drew these force directions. Right? We used the fact that charge 2 is negatively charged to draw these attractive forces. And that's all you need the charge for in a force problem, to draw the force directions. At this point, these are just magnitudes. We just need numbers for this and this. Right? So the net force, I have it written out. I'm going to go ahead and just pause this for a moment while I run that calculation here and see what I get. Okay, folks, I'm back here, and hopefully, I've got this calculation done, and I believe it's done correctly. So when we calculate a value for this piece, we get 3.38 newtons. When I calculate a value for this piece, I get 0.5 newtons, and add those things together, and we get positive 2.88 newtons. Now, the fact that it's positive, remember that when I added these, I had called left positive, so that is implying that the net force is 2.88 newtons to the left. Now, some advice on how to run the numbers. These things are quite complicated as far as, these calculations. There's a lot of buttons you have to press, and every time you have to press a button, the probability of an answer goes up. My advice is this: in your calculator, do the numerical values and do the powers of 10 in your head. And here's what I mean. In your calculator, I would type in this number, this number, this number, divide by 0.2 squared, right? I would take a minute and do that, and if you do that correctly, let's see, you get 9 times 3 times 5 divide by 0.2 squared. You can type that all in one deal. You should get 3375 if I worked it that way. Again, 3375. Now, I'm just going to do the powers of 10 in my head. 10 to the 9th times 10 to the minus 6 is 10 to the 3rd power, times another 10 to the minus 6 is 10 to the minus 3rd power. So the numerical answer of this term on the left is 3375 times 10 to the minus 3rd power. That would put the decimal right there. That's why I wrote 3.38. I rounded at that point. I think if you get in the habit of doing this, do just the numerical values and the powers of 10 in your head, you'll find that it'll be much easier to work these. You'll be faster and more accurate. You can do those powers of your 10 usually more accurately than a calculator, because in order to do it with the calculator, when you look at all the buttons you have to put, times 10 is 10 to the 9th power. There's 1, 2, 3, 4. There's like 5 buttons. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You have to type like 16, 17, 18 buttons to put those powers of 10 in. And every time you have to press a button, you're increasing the probability of an error. So that's my advice with these Coulomb force problems, or with electric field calculations, where you're calculating KQ over R squared. I would run all the numbers in front and do the powers of 10 in your head. So hope this example helps demonstrate how to calculate the Coulomb force on a particle. So what this means, we have found that the net force on this particle, due to these other two charges here and here, is to the left at 2.88 newtons. Hope this video helps. Have a great day.